Hello, everyone. Thank you for being here today. I'll be walking you through the work that I have done to predict bankruptcy in Taiwanese firms using random forest regressor. I'll also discuss how I ensured fairness, reduced bias, and improved the interpretability of our model, all while maintaining a strong alignment with organizational goals and regulatory compliance. First, let's start by discussing the responsible AI principles that I apply to the bankruptcy prediction model, focusing on fairness and bias mitigation. In the context of predicting bankruptcy, it is crucial that the model doesn't favor one type of firm over another based on certain features like financial structure or industry sector. Our model needs to be both accurate and equitable, ensuring that no firms are unfairly treated based on factors that should not influence their likelihood of bankruptcy. To address fairness, I took several steps. The first one is class imbalance handling. The data set was highly imbalanced with far more non-bankrupt firms than bankrupt ones. This imbalance could easily lead to a model that biases predictions toward non-bankrupt firms. To correct this, I applied small t, which is synthetic minority oversampling technique, and edited nearest neighbors to generate synthetic samples for bankrupt firms, ensuring the model learned to identify bankruptcy without being skewed by the class imbalance. I also use stratified random sampling to ensure that our training set maintained the same proportion of bankrupt and non-bankrupt firms as the original data, thus preserving the natural distribution of the target variable. Another challenge is bias. We need to ensure that our model doesn't unintentionally discriminate based on features like debt ratios or interest rates. For example, firms in certain sectors might have higher debt levels due to their business model, and this shouldn't unfairly influence the prediction of bankruptcy. To mitigate such biases, I applied various fairness metrics, such as demographic parity, to check for any disparate impact between groups, ensuring that our model is not systematically biased against certain types of firms. We also, by monitoring these fairness metrics, we ensure that the model predictions remained balanced and didn't unduly favor certain characteristics of firms that could lead to unfair predictions. Um, in the financial sector, particularly with bankruptcy predictions, we need to ensure transparency and compliance with ethical standards. And this is very crucial to keep in mind that of our regulatory compliance and ethical considerations. By applying these fairness measures, we not only align with ethical guidelines, but also ensure our model adheres to industry regulations around non-discrimination and transparency in automated decision-making. Next, I will discuss how we made the model interpretable. Transparency in machine learning model is crucial, especially when the stakes are high, such as predicting bankruptcy, where decisions can significantly impact a company's future. To make our random forest regressor interpretable, I implemented 5 key RAI methods. The first one is SHAP. SHAP values were used to explain how each feature contributed to a model's prediction. This provided us with local explanation showing exactly how features like debt ratios and interest rates impacted the bankruptcy prediction for each individual firm. Um, Next one is partial dependency plots. They helped us visualize the relationship between key features such as debt to net worth ratios and the predicted likelihood of bankruptcy. We could clearly see that as debt levels increase, bankruptcy likelihood also rises, reinforcing our business understanding. The third one is LIME, which is local interpretable model agnostic explanation. It was used for local instance level explanation, revealing that higher interest rates and debt ratios significantly impacted the likelihood of bankruptcy for specific firms, making the model's decision more understandable. Uh, Next one is permutation. This method quantifies how much each feature, like net income to total assets, influence the model's predictions. By examining feature importance, we gain clarity on which financial factor were most predictive of bankruptcy. The last one is ICE plot, which is individual condition expectation plots. They allowed us to assess how individual instances were affected by variations in specific features like pre-tax interest rates. We saw that once interest rates exceeded a certain level, the likelihood of bankruptcy sharply increased, providing valuable insights for financial analysis and decision makers. By applying these interpretability techniques, we were able to make informed decisions because the transparency into modeled predictions help ensure that we are making decisions based on the most impactful financial metrics. We are also able to build trust because stakeholders and regulators require transparency in automated models. By providing clear insights into how decisions are made, we build confidence in the model's output. Um, also, we ensure regulatory alignment because these interpretability methods align with regulatory compliance by making the model's decision-making process understandable and auditable. Um, Now let's talk about business impact and high-level insights. The model's predictions have the following direct business impact. The first one is risk mitigation. By predicting bankruptcy risk accurately, the model helps firms take a proactive measure such as restructuring or seeking financial assistance, which can reduce the risk of financial collapse. Also, we make informed decision making because executives can use the model's insight to make data-driven decisions about investments, mergers, and acquisitions. The third impact is regulatory compliance. Ensuring fairness and transparency helps the organization comply with regulations around automated decision making and avoid legal pitfalls. So in conclusion, by applying responsible AI principles, we have created a model that not only predicts bankruptcy accurately, but also adheres to fairness standards and provides transparency. By making the model interpretable using SHAP, LIME, PDP, permutation, and ICE, we have ensured that stakeholders can trust the model's decision. Some next steps that I suggest include further improving the fairness through continuous monitoring and bias mitigation, and also enhancing interpretability with even more advanced techniques to ensure that all decisions are explainable and justifiable. Thank you for your attention, and I look forward to discussing how we can implement this model to drive value and reduce risk in our organization.